So we are going to talk about Linux system programming, where we learn about introduction to process environment. The processes are the most fundamental abstraction in the Unix system after files. Means everything in Linux is a file. If it is not a file, it must be a process. An object code in execution. Process is an object code in execution, which is active, alive, running program, or a process is more than just assembly language. A process is an active, alive entity. It is called active, alive entity because it is going to be allocated with the processor. Okay, it will consist of data, resource, state, and a virtualized computer. Now, it will contain data in the data segment or stack segment, code in the code segment, process state, and various other things. Now, Unix and Linux took an interesting path that is one seldom traveled, and separate the act of creating a new process from the act of loading a new binary image. Now, there are we say create a process, then we get a impression in our mind that okay, there is something in the secondary storage that will be loaded in the program memory and will start executing. Well, that's not everything about creating processes. Creating processes have two separate things. One is to load a program, and second is to create the process. Creating process in loading program means a program in loader in the operating system called loader will be invoked, that will pull the program out of the secondary storage and push it into the memory for execution. Second task, allocating space in the memory for the incoming process, initializing its task structure, allocating resources is the task that is put under creating a new process. Okay. Most operating systems offer a single system call to start up a new process, but the Linux and Unix operating system do two different things. One is to load the program, and another is to create the process. Now we need two different calls for that, a fork and an exec, to load the program and create the program. Okay, we will see both one by one. The process is what? The process is actually an address space with one or more strand of execution within that address space. Now, process is nothing but a region of memory that is occupied in RAM for execution. A region of memory occupied in a region which looks like this. A region of memory occupied in RAM is called a process, and this region of memory occupied by your program for execution in memory, this region is called process context. It is called process context. Process context is the region that is occupied by your program for execution memory, and all the required system resources that are required for the program to execute are also allocated to it. This is the whole process context. Let me copy this only. So this is your process context. You see here. The process context is divided into various segments. Like this is your stack segment. The library segment in which you keep program libraries. The data segment. And the code segment. So there are these 4 segments that you have in your program. The code, the compiled code that you would have written and you would have compiled, that compiled code goes in the code segment. All the local data that you create in your program goes into stack segment. All the libraries that you use in your program like printf, scanf comes in the library segment. And the global data or the dynamic memory allocated data comes in the data segment. So these are the segments you have. The stack segment, the library segment, the data segment, and the code segment. Okay. The size of this process context, total size of this process context from here to here is always 64 GB. Now when I say that the size is 64 GB, I do not mean that it will need 64 GB of memory to execute. No. What I mean is, it will have 64 GB of addresses, and that those addresses may not have locations. So when you have addresses but you do not have locations associated with those addresses, such addresses are called virtual addresses, virtual memory. Now every process will have a task structure as well. The task structure in which you will keep information about the process. All the information about the process, like the process ID, parent process ID, who created this process, the program counter, and various other attributes of the process are kept in the task structure. It contains a lot of information about the task structure. The task structure is a kernel data structure found in a file called sket.h. Sket.h. Have a look at this sket.h here. We go inside kernel. Watch the path. User, src, kernels. Then we need kernel version. The kernel version that is working here is the kernel sources that we have is Linux 5.10.22. Inside this you will find include folder. Inside that you will find Linux folder. So this is the path, pwd path. User src kernels, Linux, include Linux. Linux kernel version, include Linux. This is the path. At this path you will find a file called sket.h. This is it. Inside this sket.h, you will find a structure. Struct task underscore struct. Here it is. Struct task underscore struct. Okay. Now this is the structure that contains information about the process. Okay. That is currently executing. Just watch what kind of information, what all kind of information do we have in the struct task struct. The very first thing it says is that thread information, which tells you information about the currently executing process. You have the state of the process. This is a reference to the stack segment, the usage statistics, flags, process trace on which CPU core it is executing. It gives you that CPU core. Okay. Then the CPU ID. It also tells you about various other priority. What is the priority? Static priority, normal priority, real-time priority, all kind of priorities are given here. Okay. Scheduling information. It gives information about RCU updates, read copy updates. Now look at these two things, and active These are important. Both have struct data structure. This is memory management. Now this refers to the memory that is being used by your program for execution. Both and active will refer to your process context, contain starting address of the process context. Okay. Then the cache information, the exit state, and the scheduling information, and various other information are there. Like this field contains your process ID. Okay. And this is thread group ID. DGID. We'll learn about threads later in the same project 3, system programming. All the threads that will be created in the program will have thread ID, and the thread ID is stored here. Okay. Now this is the reference to task structure of the parent or the real parent, the process that created your current process. And these are the processes that are spawned or created by your process. So various other information is there, and we will see all this information about the process one by one. This field is the name of the process. Okay, this is information about the files that has been opened by your program. So like this it works. The interrupt information, hard IRQ, soft IRQ. Okay, so this is how lots and lots of information is there about each and every process that is executing in your machine. Okay, this is task structure for each and every process that executes on your machine. Okay, so how many processes are actually executing in your machine right now? Yes, all executing. So many processes are executing. So every process that is executing will have a task structure. Right now so many processes are executing, isn't it? And every process will have associated task structure. Okay, and will execute. Huge data structure, isn't it? Task structure. Now the task structure contains some important information like state of the process, a reference to the stack. It contains the process ID. It contains the parent process ID who created your current process, the real parent or the other parent. It contains a program counter which keeps track of which statement to execute. It keeps information about the that is the pointer to the process context, active I'll tell you the difference between these two later. Thread group ID, the name of the process, list of open files, and signals. What are the signals being used in a program? Starting address of process context are and active These two. Okay. So this is about task structure. Now getting into processes, how to create the process. Every process will have process ID. The very first process that is created in our system is the init process that will have process ID 1. And before that there is another process that has the process ID 0 also. Okay. Every process will maintain its own program counter. Okay. Own program counter. It will keep the record of which statement to execute next. You see the process have program counter PC. The program counter, suppose your process goes from 0 to 64 GB. Okay, within that this portion, let's concentrate on this portion, code segment. Suppose the code segment goes from here to here. Suppose the 64 GB, the code segment goes from 10 to 12 GB. Huge code it is, isn't it? So the program counter will move from 10 to 12 GB within this address. Okay, the program counter will move from 10 to 12 GB only. This is the region that is fixed by for the code segment, and the program counter will move only in the code segment and refer to the instruction to be executed next. There is a special set of files in a directory called proc. There is something called /proc. This we will discuss later. Okay. To look at the program process table, the process table is a table that is maintained in the kernel for every process that is executing the system. Now the process table, you can see the process table using ps-ax. Okay. Now the maximum number of processes that could execute in your machine could be generally it is 32768, but you can see in your system what is this limit at this point. /proc sys kernel PID max, that is 41,94,304. So all the books all over the world say that the maximum number of processes that could be created in your machine is 32,768. That is theoretical, but my system, that is a Linux 5.10 installed on a 8-core processor, can create 41,94,304 processes. So the number of processes that could be created is not a restriction by Linux. Instead, it is a system dependent parameter, which is a variable. Okay. So how many processes could be created in your machine? The answer is this path, this file, proc sys kernel. Inside proc sys kernel, you will find a file called PID_max. Maximum number of processes. Is found in this file, and that changes from system to system depending on the system configuration. Okay. This is it. For Linux 5.10, that is my machine, on x86 i7 processor with 8 cores. That is the configuration of my machine. At this machine, you find that this number of processes to be executed to be 41,94,000 and something. You see that? So it is a system dependent, and it is not a static fixed value that could be just given like that. Okay. Now, the process hierarchy. The process ID, every process that executes has a process ID associated with it. Okay, every process that executes have a process ID associated with, and the data type of the process ID is a kernel data type. The data type of the process ID is not some integer, char, float. These are data types that are defined in C, but the kernel have its own data types. Okay, so the data type that is used to describe the PID, process ID, is called PID underscore T. Process ID underscore T means type, and this process ID is defined in a header file called systypes.h. So you have to include the systypes.h every time you use the process ID, and the data type is PID that refers to the process ID. Now, if you want to obtain the process ID of any process in your system, you will use this system call getPID. Okay, the getPID system call returns the process ID of the invoking process. Okay, so this is going to be the very first program in our system programming, where we'll write a program in C that will return the PID of the process. Here you see. Now, the process ID. Here it is. Look at this program. When I execute this program, I am printing the process ID of a program. And there is another call associated with it, that is getPPID, get parent process ID. GetPPID gives you the ID of the parent process. The parent process is the process that created the new process. So there is a process that creates a new process. The hierarchy goes like this. Suppose you have your shell here executing. Shell is a process, and this process creates a new process. So the new process also execute. Say the process ID 100. Then the process ID 100 creates another process, and another process also executes. Say process 101. Okay. So if you look from this perspective, from here, this is ordinary process. Creates a new process, then the new process is the child process. If this is the child process, then this is the parent process. Okay. For the parent process, for the child process 101, this is parent and this is the child. So the creator process becomes the process parent process, and the created process becomes the child process. Okay. So the creator process will be the parent process, whose ID will be fetched using getPPID, get parent process ID, and the child process, that is a new process, that is or any process can get its own PID using getPID. So in my program I'm printing the PID, obtaining it from getPID. I am printing the parent process ID, obtaining it from getPPID. Okay, I'm also printing the function name here, as you can see. Okay, so these header call, these getPID and getPPID are defined in unistd.h. Okay, will be used to display the current process ID and its parent process ID. You can also use man3. Man. Open the man page for the manual page. Now the manual page, for the manual page, tells you the various categories of the man pages. 1, 2, 3, 4, 5, 6, 7, and 9. There are these 9 categories. Okay. Now, what are these categories? The category number 1, man 1, will give you all the executable programs or shell commands. Means if you want to know the manual page of the shell command, see the manual page of the shell command, you can use man 1. Man 2 is used for system calls. Man 3 is for library calls. Okay. Man 4 is for device specific files. Man 5 is for file formats and conventions. We'll see all with these one by one. Okay. Man 7 is for various packages. Man 8 for system administration commands, and man 9 is for kernel routines. So I'll be using man 3 to show you the library calls for getPID and getPPID. Wait. Man 3 getPID. Here it is. Okay. This is POSIX programmer's manual. That is for us. getPID. Description. Return value. Shall always be successful and no return value is received to indicate error. Okay. No errors are defined. Isn't it? So it gives you the process ID. Shall return the process ID of the calling process. Right? So that is what we are going to use now. You can also use getPPID. Return the parent process ID of the calling process. Okay. So let's try this program here. Run. There you see the PID and the parent process ID and the current process ID. Current process ID is this, and the parent process ID is who created this process was 4507. Okay, like this you print the PID and parent process ID. You'll need it very frequently in your program. Okay. Then there is another system call called system. Before that, let me give this to you in Jamboard because you have to write a program for this. Oh, is it visible to you? I hope it is visible. Or shall I change the background? Hold on. I hope it is visible to all of you. Okay, and for PID and getPPID, watch this and watch this. Okay, to know more details about this, you will use man 3 for getPID or getPPID. To know more about this. Then there is another system call that I would like to introduce to you. That is called system call system. Now system call system is used to create new processes. Till today you have created new processes from shell. That is, from shell you run some program using /arrowtout and things like this, and the new program is created. But when you use system call system, then using the system call system you can create new process from your already executing process. If you look at the man page for this, man 3 system now creates a new process that executes the shell command specified in command using ACL. So description is slightly complex here. I'll simplify it and explain it to you now. The system call system is basically used to execute a new program from the currently executing program, like this. Suppose you have a program executing, okay, then from that program you have to start a new program. Then the path of the new program has to be given. System call system, first of all let me tell you about this. Creates new program or process from currently executing process. Okay. The second argument, this is the path and name of the new program. How it works is like this. From the current program where you are executing, you will suppose this is the program that you are executing, current program. You give the system call system and the path and the name of the new program, then the control goes to the new program and new program starts to execute. While the new program executes, the old program waits for the new program to finish its execution. When the new program will finish execution, then the control will return to the existing program, and then the existing program will proceed further. So this is how you can create a new program from the currently executing program. More details about how these programs are created will be given to you later on. Okay. Right now let me show you few more examples about PIDs first of all. I would not like to miss it. So here I am going to create the process. I show you the process ID using getPID. The file name using __ file __. The function name using __ func. All these three things I think you have used, or maybe the file file macro is new to you. Just see, it will give you the file name as well. There it is. It gives you the file name, the process ID, everything, isn't it? Let's see another example where we are going to print the PPID. Here it is. The PPID, PID, file name, function, everything will be printed. The PPID will be printed using getPPID. The PID will be printed using get PID and the file and the function macro. So the PPID will also be printed. You will be able to see it here. The PID and the PPID, everything is printed using get PPID, get PID, underscore underscore, FILE underscore underscore, and underscore underscore, FUNC underscore underscore to print the function name. Okay. Then system call system. Watch this. So I'm printing the get PID, will print the process ID, underscore underscore FILE underscore underscore will print the file name, underscore underscore FUNC underscore underscore will print the function name, and then in the next line I have used the system call system, and then this is the path and the file name of the program that I want to run. Path and file name of the program. The path and file name of the program, as is given here, will execute. But you don't see a path here. If you don't see a path here, then the control goes to an environment variable. Okay. Important point. If the path is not given, then the control goes to PATH environment variable that contains standard paths. Okay. Now standard paths are like /bin, /usr bin, like this. Like usually your system commands are kept there. Okay. The control goes to path environment variable, which contains standard paths, and the given file is searched there for execution. Okay, so this is how it runs. Like in the case of ls, I have not given the path. You see, I have not given the path. Because I have not given the path, therefore ls will execute by control jumping to the path environment variable and trying to locate ls there, and it will find ls there and execute it from there. I'll just run this program for you to see this. What happens when I run this program? It says PID file function begin. So this statement executes. Then the ls program is fetched by the system call system and is executed. So this is the output of ls. Then the end statement. Here is your end statement there. So the program begin and the program end, and this is how you can execute a new program from the current existing program, or this is how you can execute Linux commands from existing program. system call system. Okay, more about this system call system. One more example we'll see. This. Yeah. So in this program, I'm executing the begin statement and the end statement. In between, I have system call system, in which I'm executing ls command with options -a -l. So you can also supply options to the programs that you will execute. So these options will be taken by this program at runtime. So you see, when I compile this and run this, it will take options as well. There you see the ls output in the long all format. All long, all displays the hidden files also, and all the output is given in long format, and towards the end you have the end statement. So the system call system not only take the program name but also the options or the runtime parameters. We'll see one more program in this. Yeah. Look at this program carefully. I am using the system call system to run another program. Now another program is not some command. Another program is your own program called upper. Let me show you the upper program first. There it is, upper.c. This is your upper.c program. What will you do? Look at the line number 10 carefully. Look at this line number 10 carefully and try to understand. We will print PID using get PID. We will print parent PID, file name function, also parent PID using get PPID, file name using file and the function. And after that, this program will print again PID, PPID, file name, function, and then it will give you the prompt, enter a string. Press Ctrl D to end. You have to enter a string. So in line number 13, you will start entering string using getChar. You have done this. Okay. Ctrl D is end of file. So unless the character is not end of file, you keep on entering. When you press Ctrl D, entering is over. Every time you enter a character, that character is converted to uppercase and is displayed. That's it. And when you press Ctrl D, it will be over. The program will be over, and then the control will return back to your main program from where you had invoked the upper program. Okay, so in one way you are creating another program from the current program, the upper program. Let me compile the upper program first, because we will need the compiled version of upper program. The upper program is compiled and is listed here. Now I will execute this program, number 4. Run now. There you see. The program number 46 PID file is 04system.c, function main begin, and it creates a new program using system call system. Program number is 77, new program, whose parent PID is current program. File name is upper.c, function name is main begin, and it says enter string. Okay. I say congratulations. You begin. See, converted to uppercase and printed. System programming today. I wish you. See, converted to uppercase. Good luck. Control D. The control returns to the current program and the current program executes. Okay. So this is how the system call system works. Right. So this was your first hand introduction to the system program wherein I tell you about the process ID, parent process IDs, the process context, and how to create a new program from the currently executing program. You have been creating new programs till date, but writing it from the shell ./a.out and something like that. You're running all the new programs from shell. But now you can run new programs from currently executing programs as well. And you can also run Linux commands from the C programs as well. Isn't it? So that was a good beginning, and that's all I got for you today. Please refer to the Jamboard. The three things I mentioned essentially: the PID, PPID, get PID, get PPID, and system call system. Try all these one by one. Try all these three calls one by one. Okay, and ensure that you're on par with me and you're not lagging behind in system programming. Fine. So that's all I got for you today, and I wish you good luck in system programming, and have a nice day ahead. Thank you.